Hello all. So today we are going to discuss about measurement of energy part 3. Okay. So in this lecture I am going to discuss about single phase induction type energy meter. Single phase induction type energy meter and the torque equation. Okay. So this is a diagram of the circuit diagram or schematic diagram of the single phase induction type energy meter. In this there are two magnets. Okay, there is a shunt magnet, this one, and a series magnet, this one. Okay, a shunt magnet and a series magnet are there, and in the center limb of the shunt magnet, as you can see, there is a coil. Also, in the two limbs of the C-type series magnet, there are two coils, and the energy we need to measure is given across this pressure coil. Okay. Or the two ends of the pressure coil is connected to the supply, and the current from the supply is energizing this pressure coil and thereby making this shunt magnet an electromagnet. Okay. So the energy or the current flowing through this pressure coil is proportional to the supply voltage. Okay, this is proportional to supply voltage, or the flux produced by this shunt magnet, or the 5P pressure coil. So the flux produced by this magnet is represented as 5P. This 5P is proportional to the supply voltage. Okay. Similarly, this series magnet is also wound by a coil, and this coil is energized by the load current. Okay, that is the current which energizes the coil, or the current which makes this magnet an electromagnet, is load current. Okay, and the flux produced by this electromagnet is phi s. It is represented as phi s. Okay, that is series magnet. Therefore, this phi s will be proportional to the energizing quantity, and the energizing quantity is load current. So phi s is proportional to load current I. Okay. And as I have explained in the previous lecture, the induction type meters will be having an aluminum disc in center. Okay. Similarly, here also an aluminum disc is placed in between these two magnets like this, and the center of this aluminum disc is fixed to a spindle, and the end of the spindle is, one end is connected to the recording mechanism and the other end is fixed in a pivot and jewel bearings. Okay. So there is an aluminum disc kept in between the two magnet, that's shunt magnet and series magnet. Okay, and the energy to be measured is given across the pressure coil wound like this. Okay, and the load current is supplied through this series coil, thereby energizing it, and it produces a flux phi s, and this magnet produces a flux phi p. Okay, and due to the interaction of these two flux on this disc, what will happen, as I have explained in the previous lecture, what will happen when two fluxes interacts here? Okay, due to the flux phi p, an EMF EEP will be there and a current will flow. Similarly, due to this flux phi s, an EMF EES will be there and a current will flow through this. Okay, and due to the interaction of this flux and the current produced due to this flux, a torque will be there. Similarly, due to the opposite quantities, and another torque will be there, and due to the effective of these two torque, we will get a deflecting torque. Okay, that is due to the interaction of phi p with the current IES, due to the interaction of flux phi p and the current IES, we will get one torque, and due to the interaction of phi S with the current IEP, we will get another torque. Okay, and the resultant of this two torque, we will get our deflecting torque. Okay, so this is the principle. Okay, now let us validate it. Let us move on to next slide. Okay. Construction of this single phase induction type energy meter. Okay. First, it is having a driving system. Driving system means the system that will make this energy meter to move. As we know, there is a moving element within this energy meter, or this energy meter is a motor type meter. Okay, therefore something is driving it, and that system is driving system. So here, what is driving system? It is having two electromagnets, series and shunt, as I have told, and both these electromagnets are made up of silicon steel laminations, and the coil wound on the series magnet is current coil, which is excited by the load current, and the coil wound on the shunt magnet is pressure coil, which is connected across the supply and carries the current proportional to the supply voltage. Okay, and as you can see here, there is a blue bands here. This is a copper band, copper shading band. The need of that I will explain later. Okay, so adjustable copper shading bands are provided in the central limb of the shunt magnet. Okay, so this is this driving system construction. Clear? Now let us move on to the moving system. What is a moving element in this energy meter? The moving element in this energy meter is rotating aluminum disc. Okay, so there is a rotating aluminum disc which is mounted on the spindle placed at the center, and the bottom of the spindle is provided with pivot and jewel bearing, and the top of the spindle is connected to recording mechanism through a pinion. Okay, recording mechanism means there will be a pointer or something, or gear, or a pivot and jewel bearings. In this case, it is an energy meter, therefore we will be having a recording mechanism. That is, number of revolutions will be recorded, and the energy will be displayed. Okay. So here, instead of the pointer mechanism, it is a recording mechanism is there, because it's an energy meter. Okay. In floating shaft energy meter, an aluminum disc is suspended freely between the two magnets attached to the shaft. Okay. That is, there will be no spindle there. In the floating shaft energy meter, there will be no spindle, but aluminum disc is suspended freely between the magnet. There will be a shaft to the end, but there will be no attachments to this aluminum disc. Okay, that's why they are called as floating shaft energy meter. Okay, there will be shaft will be there. Two magnets will be attached to a shaft, but the aluminum disc will be freely rotating in between them. Floating. It will be in a floating manner. Okay. So there is a moving system. Now let us move on to braking system. Okay. In our normal measuring instrument, I have told, in order to stop the rotation, or in order to stop the deflection within the meters, we need some controlling mechanism. Okay. So in the energy meters or induction type energy meter, single phase induction type energy meter, we need to stop the rotation of the disc. Then only the recording will somehow recorded. Okay. Or we need to, at some point, we need to break the system. Okay. And we need to record the number of revolutions, like that. Some necessities are there. So for that, braking system is required. So here, for that purpose, we are providing a braking magnet. This one is a braking magnet here. We are providing a braking magnet. I will show you it in first diagram. So here you can see this is a braking magnet. Okay. So what will happen when we place a magnet like this here? When we place a braking magnet like this, what will happen? There will be a magnetic field in between the two poles of this magnet, and this magnetic field will interfere or will distort the operating magnetic field present in this aluminum disc. As a result, what will happen? As a result, an EMF and a current will be induced and a torque will be produced. Okay, due to this braking magnet, a torque will be produced, and that braking torque will be opposing the operating torque. That braking torque will be in a manner such as to oppose the operating torque. Okay, and this will cause the braking effect. Okay, so here, braking magnet is so placed that the disc revolves in the air gap of the two poles of the magnet, and this magnetic field induces an eddy current in the disc which react with the main magnetic field and create braking effect. Okay, by changing the position of this braking magnet, we can adjust the speed of rotation of the disc. Okay, we can even adjust the speed of rotation by changing the position of this braking magnet. Okay, so that is about the braking system. Now let us move on to registering system. So this is one of the main thing. Okay, we need the energy that is recorded should be displayed to us. So how it is doing? That is explained in the registering system. So registering system consisting of train of gears, driven pinion and worm gears. That is, in this energy meter, what we are doing? We are calculating the number of revolutions that the disc has made over a period of time. Okay, and from this number of revolutions, the energy it drawn is calculated. Okay, and for the indication of this energy, it has many dials. Okay, as you can see in this figure, this is our energy meter display like this. These are actually gears 1, 2, 3, 4, 5. Okay, 5 dials are there, and this will indicate the number of times the disc has turned. Okay, that is, it will indicate the energy, and each of this dial has a unit. The right hand dial pointer, this red one in the register, indicates 1 kilowatt hour. Okay, so what is coming here? If it is 1, it is 1 kilowatt hour. If it is 2, 2 kilowatt hour, like that. Okay, and the second dial indicate 10 kilowatt hour, and if the first dial is 0 and the second dial is 2, then 20 kilowatt hour. Okay, likewise third one is 100 kilowatt hour, fourth one 1000 kilowatt hour, and so on. Okay, so in this manner it is registering the energy measured. Okay, so it is not the number of revolutions. Actually, it will internally calculate the number of revolution, and after this n number of revolution, 1 kilowatt hour will be recorded. That will be a constant of the meter, and depend upon that, here the dial turns. Okay, after n number of revolutions, one movement will happen likewise in such manner. Okay, now moving on to operation of the single base induction type energy meter. This is what I explained at first. Actually, the flux produced from the shunt magnet 5P will be resultant of the flux produced by both the pressure coil and the lag coil. Okay, that is, in the shunt magnet we have two coils actually, one copper shading band and the pressure coil, and the resultant flux from the shunt magnet will be the resultant of these two fluxes. Okay, that is pressure coil and the lag coil 5PT and 5L, and this flux 5P will be in quadratio with the supply voltage. Okay, this flux 5P from the shunt magnet will be in quadratio with the supply voltage. Okay, as it is energized from the supply, it should be in quadratio with the supply voltage. And the flux produced by the current coil 5S is proportional and in phase with the load current. Okay, these are the necessities actually. 5S is proportional and in phase with the load current. The flux 5P induces an eddy EMF EEP, which in turn induces an eddy current IEP, Similarly, the flux phi s from the series magnet induces an eddy EMF EES, which in turn induces an eddy current IES. The interaction between the flux phi p with the eddy current IES produces torque 1. Similarly, the interaction between flux phi s with the eddy current IEP produces torque 2. And the resultant of this torque, these two torques T1 and T2, will produce deflecting torque TD, which will cause the rotation of the aluminum disc. Okay, just note it down while you are learning it. Now this is a phasor diagram of the single phase induction type energy meter. Okay, this is similar to the diagram which I have discussed before in the induction type energy meter type induction type instruments. The energy meter, the phasor diagram we have learned there, it is same as this. The difference is that there we have mentioned the angle between the two fluxes as beta. Now here instead of that we have another angle delta. Okay, and here in this case the beta is delta minus phi. So we can find the torque equation of this single phase induction type energy meter by replacing the beta in the previous previous equation with delta minus phi. Okay. So in this phasor diagram, you can see here this V is the supply voltage, I is the load current, and phi is the angle between the V and I, phase angle. Okay, and this phi s is the flux produced by the series magnet. Phi p is the flux produced by the shunt magnet. Okay, and IP is the current through the pressure coil, and IE pressure coil, which is in phase actually. Okay, and IEP is the current induced current within the aluminum disc due to the flux phi p. Okay, and IES is the current induced in the aluminum disc due to the flux in the series magnet phi s. Okay, and EEP is the EMF induced in the aluminum disc due to the flux phi p, and EES is the EMF induced in the aluminum disc due to the flux phi s, and alpha is the angle between the induced EMF and the corresponding current. Okay, so this is the phasor diagram, and in order to find the torque equation, we should have an outlook of the torque equation in the induction type instrument. In that instrument, the first torque is given by this phi 1, phi 2, F by Z, and cos of the difference. So here, what is the angle between the first torque inducing components? First torque is induced due to the interaction of produced due to the interaction of what? Interaction of phi p with IES. Interaction of phi p with IES. Okay, phi p with IES. Similarly, second torque is produced due to the interaction of phi s with IEP. Okay. Now you just move on to the induction type meters torque equation. In that, our equation was our phase difference between the IEP and phi s. Okay, it is cos 90 minus beta plus alpha. Okay, you can see it, cos 90, that is phi 1, phi 2, F by Z, cos 90 minus beta plus alpha. In that equation, let us replace here beta with delta minus phi. Okay, let us replace the beta with delta minus phi and phi 1 and phi 2 with phi s and phi p. So you will get the torque equation of the first torque here. Okay. Similarly, in the second torque equation, replace the beta with delta minus phi. Okay, so you will get the and phi p and phi s with phi 1 and phi 2 with phi p and phi s. So you will get this equation for second torque. Okay, and now take the resultant of this two torque. You will get this equation here. Okay, in the first case, induction depth meters, our equation was deflected torque is equal to K1 phi 2 F by Z sine beta cos alpha. So replace the beta with delta minus phi. So you will get this equation. And as I have told, the flex phi P is proportional to the supply voltage V and flex phi S is proportional to the load current I. So let us replace this 2 with this one, this V and I, and let us change the constant from K1 to K2. Okay, now let us consider this F, Z and alpha as constant. It will be usually constant. F frequency, Z eddy current frequency, F is frequency and Z is the impedance of the eddy current part. So it will be almost constant. So considering F, Z and alpha is constant, we can change this constant K2 to K3 like this, and cos alpha will also go into this constant. So deflecting torque get reduced to K3 into Vi sine beta or K3 into Vi sine delta minus phi. Okay. Now, if n is our steady state speed of this aluminum disc, let us consider n as the steady state speed of this aluminum disc. So in that case, how much braking torque is produced will be in proportional to the speed of the disc. Okay, that is TB will be proportional to the steady state speed of the aluminum disc. So let us move this proportionality with this constant K4, that is TB braking torque TB is equal to K4 into N. Okay. Okay. Now, when will our instrument will record the value, record the measured value? When the driving torque becomes equal to the braking torque. That is, when the deflecting torque becomes equal to the control torque, our measuring instrument records the value. So, in this case also, when this deflecting torque or driving torque TD becomes equal to the braking torque TB, the recording happens. So, let us equate this equation with this equation. Okay, so we will get our new equation as n is equal to what? N is equal to K3 divided by K4. N is equal to K3 divided by K4 into Vi sine delta minus phi. That K3 divided by K4, let us change it as new constant K. K is K3 divided by K4. Okay, so steady state speed is obtained as K into Vi sine delta minus phi. Clear? So in this equation, in order to obtain the maximum speed, what is the necessary condition? Delta should be 90 degree. Okay, so sine delta minus phi will come as under maximum conditions sine 90 minus phi, that is cos phi. So our equation becomes steady state speed n is equal to K into Vi cos phi, and we know that Vi cos phi is power, right? So n is equal to K into power. We obtain the steady state speed is proportional to power. Okay, but what we need to record? We are recording the number of revolutions, right? So in order to obtain the number of revolutions, what we should do? We should integrate the speed. So for that, total number of revolutions is obtained by integrating this equation. That is integrating K into power. Okay, let us take the K outside. So K into integral of power into dt. So what is the integral of power? It is energy. So we have obtained that total number of revolutions is equal to K into energy, or the total number of revolutions, if we recorded, it will be proportional to the energy to be measured. So due to that case, we are recording in total number of revolutions here. Total number of revolutions is proportional to energy. This is what we need to prove in this case, in the case of single phase induction type energy meter. Okay. Okay, dears. So this is the torque equation and the relation of the induction type single phase induction type energy meter. It is one of the important derivation also. You should do it in your work note and should try it. Okay. Construction and torque equation we have discussed. In the next section or in next lecture, I will discuss about the various error compensations in the single phase induction type energy meter. Okay, this will be the last topic of this module, error compensation in the energy meter.